Stability and predictability in dynamically complex physical interactions. In daily life, humans frequently interact with the environment by using tools, typically rigid objects such as the spoon, but when the spoon is filled with soup, it becomes a dynamically complex object. A very similar example is carrying a cup of coffee, where the fluid adds complex interaction forces and makes the task challenging. In fact, these interaction forces can become unpredictable. It is commonly held that humans develop internal models of their own body and the objects in the environment. However, when these objects become unpredictable, how do humans manage this? We hypothesize that humans seek to make interactions predictable. Predictable interactions are operationalized by stable interactions. In this complex system, we use contraction analysis to assess stability or convergence of trajectories in state space. Specifically, our task is transporting a cup of coffee, greatly simplified to a two-dimensional conceptual model with an arc and a ball rolling inside. This is equivalent to the well-known cart and pendulum model, where the cart slides on a horizontal line and a pendulum is attached to it. This model is implemented in a virtual environment where the human interacts with this system by a robotic manipulandum that exerts forces on the cart moving in the horizontal direction. The specific task is to move this cup of coffee from box A to box B. On its way is a perturbation that is visible, and this perturbation presents a force either against the motion direction or in motion direction, assistive or resistive. Analysis of state space trajectories look as follows. Here you see the blue line, which is a trajectory of one trial. P minus and P plus is the onset and offset of the perturbation. The yellow areas are the convergence areas. In this early trial, the trajectory does not enter the convergent areas. In contrast, later in practice, you see how the trajectory enters the convergent area at the onset of the perturbation and exits at the offset of the perturbation. We interpret this behavior as that humans exploit the convergence properties of these areas to stabilize their unstable system. We conclude that humans exploit contraction regions in the face of perturbations and propose that this is a method also useful in robotic control